video is a continuation of our memory investigation that we started in the last video. In the last video, we collected 2 heap snapshots of the PerfView tool itself to do an investigation. This first one was collected when after we'd opened an ETL file, and this second one we collected after also opening a stack viewer and then closing it again. And we expected those two to have the same memory amounts, but we noticed that in fact the baseline had only 16 megabytes. Whoops. And the after image had 27. So we're trying to figure out what's going on there. And the way you do that is use the diff feature of PerfView. Once you've opened 2 stack viewers, you can click on the diff of menu item, and it will show you every other stack viewer that's currently open and ask whether you want to diff it with that as a baseline. So I'm going to pick that second after shot and then use the baseline of the first one, and it will form this diff view. And so what this does, the way diff works, is it will take every sample in the baseline, all these samples, and it will negate their metric. So it's like it has negative memory. It won't negate the counts, it will only negate the metric, and then it creates a combined view. So in fact, if you look at the combined view, you have 650,000 items, which is the sum of this 200,000 items and this 450,000 items. But because the metric has been negated, the metrics is the difference between this 27 meg and this 16 meg is what produces this 11 meg. So this shows us what is now different between those 2 snapshots. The next thing you want to do when you're looking at a diff is to looking for negative entries. The problem with negative entries is that they represent places where the baseline is using more memory than the after image. And the problem with that is that this negative quantity might cancel out some of these positive quantities. We just don't know. Or we have to determine whether that's true or not. And as long as they're all very small, then you don't have a problem. So in this case, this one's kind of big, but it's not huge. In other words, it's smaller than these top 2 ones. So there's no way that this negative value could have canceled out these positive values. So analyzing these top 2 entries, it's probably pretty reasonable. So that's what we're going to do. So the way we do that analysis is we'll take the first one, in this case the stack source sample, and we'll just double click on it. And what that does is it brings us from the by name view over here to the ref from view. And what the ref from view shows you is what is holding this alive, which is what we're after, right? Why didn't the GC collect this? And the answer is because there's this path back to the root of the graph. And at this point in the analysis, you must know something about the program. There's just no substitute for understanding what your program's supposed to do. And I can tell you, because I wrote PerfView, that I can explain what these things are. Basically, what this is describing is, if I go to the actual viewer, this main window has a text tree view. That's this thing, and the tree view has a CPU stacks item, and that item has a PerfView stack source. That's what this PerfView stack source is. And that in turn, the way stack sampling works is that an ETL file has so much data in it, much of that data is not relevant to a particular stack viewer. So what we do is we create just what we call stack source samples, these things, which just contain the metric, the time, and the stack, because that's all we need. And then we collect a bunch of them into this copy stack source. And so the fact that when we double-clicked on this CPU stacks originally, it would create one of these copy stack sources with a lot of stack source samples makes perfect sense. And it also makes sense that it's still alive, because we actually do cache that on purpose, because we don't want to have to go back to the ETL file and fetch it again if we were to reopen this CPU view. So that is actually by design, and so we're going to leave it. But what's useful is that PerfView has told us how much that costs. it cost us 3 megabytes because we decided to cache that information instead of just recreating it. So we might decide if that number was too big and we really needed that memory back, that we should just throw it away and recreate it if we needed it. But for now, we're going to assume it's okay. So we've looked at stack source sample. We've decided that there's no issue there. So next we're going to look at this stack info, and so we double click on that and see its path back to root. This one looks much more like it's a problem. Again, in order to understand what's going on here, you need to understand something about the program. These call tree node base items here, they represent a line on this stack viewer, okay? And moreover, is because of the navigation requirements of a stack viewer, I need to be able to get from any line basically to anywhere else. So each of these nodes do point back to their call tree, and then the call tree points at everything. And they also, that call tree also points at some shared information. In particular, this information up here is information associated with this viewer stuff at the top. The patterns and the fold patterns and so forth is all up in here in this filter stack source. And we do keep track, we do remember that. The call tree does remember that information. So all of the fact that all of these things are connected together makes perfect sense. What doesn't make sense is why the tree is alive at all. Because we kind of expected, we closed the window, so there shouldn't be any references to the call tree from the window anymore, and so that whole tree should be dead. And what we're finding, well, no, it's not dead, because system component model reflect type description provider has a cache called _property cache, and it's holding on to one of these nodes. What's going on there is that whenever the GUI needs to render a line, it actually needs to fetch properties from the model, the call tree node base type, and it uses reflection to do that. When that happens, the system component model evidently remembers that so that it can do that operation more quickly the next time. That even makes sense and is reasonable. The problem is that it causes us, it's unfortunate. What's going on is because any node, any call tree node base will keep the whole tree alive. Any caching in this property cache will keep a large amount of data alive, and that's quite unfortunate. So we could solve this problem one of two ways. The first way is to try to flush this cache more aggressively. The other way is to make it so that call tree node bases don't keep everything alive. And I chose the latter because it turned out I couldn't find a way of flushing this cache. So the only alternative I had at my disposal was to basically break links. So this is what I did in this code. I created a dispose method on a call tree, and what this dispose method does is recursively call all the nodes in the tree and breaks the links that hook them together. And so now when this cache points at this call tree node base, it might keep a few call tree node bases alive, but only a few, and the rest of the call tree will die. So what I'm going to do is I'm going to close these now, and I'm going to try that fix out. So I'm going to compile this, and I've already compiled it. So I'm going to rerun perfview with the new fixed version. I'm going to open that same trace, and I'm going to open and close the stacks. So I'm going to open the stack viewer, and then I'm going to close it. So now I'm going to again take a heap snapshot. And what we're hoping for is that we'll get a better heap snapshot than we did before. So we select that, we force a GC, and then we dump the heap. And what we're hoping for is we're hoping to not see any of those stack infos anymore. And we can see, oh look, it dropped down to 25 megabytes. That's very hopeful. So I'm going to open up the unfixed version, which had 27 megabytes, and then I'm going to do a diff. And so now this will show me sort of, this will show me what's been lost, if you will. So let's wait for that diff. And again, remember, all the diff does is take the baseline, and now we expect the baseline to be negative. So we saved, oh shoot, I'm going to do the diff the other way. I'm going to diff starting with the big thing and use the smaller thing. Even though it's after it, I'm going to use it as the baseline because I like to keep things positive. And we could ignore this free field because free memory we don't really care about. So and what we see is, in fact, we did in fact reclaim a whole bunch of things. We reclaimed the stack infos, the call tree, the filter stack source, text blocks, and some other things. So this is great. At this point, we have resolved our memory investigation. So in recap, how does a memory investigation work? Basically, you want to take two different heap dumps at different points in time where the heap is growing, and then do diffs of them. And at that point, you have to start thinking about your program and understanding why things should be alive or shouldn't be alive, and that will lead to the fix.